Welcome to the next video about systems of linear equations and their solution sets. This one's about the parametric form of the solution set, and I also want to look in more detail at three-dimensional space. And in three-dimensional space, let's think about what do the solution sets of three variable linear systems look like. And let's break it down into a couple different cases. First, let's look at one equation. For example, let's say the equation is y minus z equals 2. And this equation doesn't have an x in it, but it turns out that doesn't really matter. You could think of this as just a regular old equation on the yz plane, which you could graph any normal way. But then there is still an x variable that we still didn't write down in this equation, but that x could be anything. So anytime you have a pair for y and z that makes this work, your other variable x is free to be whatever it wants. So what that looks like is going to be something like this right here, where what we're looking at right here is the x-axis is red. So if we're looking parallel to the x-axis, so we can't really see it, we're mostly just looking at the y-z plane here. And what we see is a graph of the equation y minus z equals 2 as like a line. But then when you turn sideways so that you can see the x dimension coming out, you see that from any point on the yz plane where x is 0 or anything, you can go left or right sideways parallel to the x-axis from any point, and you're still going to be on that plane. So that's my explanation for why a single equation with three variables gives you a solution set, a set of x, y, z points that makes it true, that is a plane. Now, what if you have two equations and you want to know what is the solution of that system? Here's a little example we're going to look at. We're going to start with one of the equations, but then also have an x plus z equals 2 equation. So what does that look like? Well, we can actually graph the other equation and see what the intersection looks like. And graphing x plus z equals 2 gives you something where if you ignore the y-axis by looking in a direction parallel to it like so, so you're just looking at the xz plane here, it looks like a line on the xz plane, but then if you turn it sideways, you can see that you can, from any point on this green plane, move parallel to the y-axis and stay on the plane. So anyways, where do they intersect? You can see that they intersect at what looks like this line here. And I'll try to show that line. It looks like that. And that's still an infinite number of points. So there's still an infinite number of solutions. And we're going to look at how to describe them using parametric form in a minute. But first, let's just look at the different possibilities for what it looks like. So with this example, the solution set was a line, which gives you an infinite number of solutions. And you can just, if you use your imagination, you can probably see that it's impossible to just get one solution out of two equations, because you can't have two planes that are flat that go on forever that only intersect at one point. They're either going to intersect at a line or not at all. So what does it look like if they don't intersect at all? That means you just have two parallel planes that look kind of like that, and that gives you a solution set which is empty. Or in other words, there's no solutions. So those are the two possibilities with two equations. You either have an infinite number of solutions or none at all. Now, if you have three equations, it's a little bit more complicated. And most of the time, if you have your three planes that are all kind of slanted in different ways, they're just going to meet at one point, which is what I attempted to draw here. but I found a better picture on the internet that illustrates this. So you can see the only point that is a solution of all three of the three different planes is the one where they intersect. So in that case, your solution set is just one point. Now, there's other ways they could intersect, such as if two of them are parallel in some way, or maybe they don't intersect. That could give you different possibilities, such as these ones. So you might have an infinite number of solutions if all three are parallel in a way that so that they all intersect at a line. There's an infinite number of points on that line where they intersect. Or there might be no points that are in common for all three of the planes, in which case you have no solutions. So yeah, it still works in R3. You can just see visually when you're talking about intersections of planes, you're always going to have no solutions, one solution, or an infinite number of solutions. And if you have three or more equations, I didn't actually just talk about like 4 or 5 or 6 equations because it kind of gets impossible to draw. And also, the same thing is going to be true. You're still talking about like if I took this kind of thing and I drew another plane through it, it's either going to meet this line at a point or it's just going to go straight through the line. And then the solution set is still going to be a point or a line. So this works with 3 or more equations. Now let's go over a kind of notation we're going to use, parametric form of a solution set when we want to describe something like a line or any kind of a solution set of a linear system that has an infinite number of things in it. So the trick is I notice I can solve the first equation for x in terms of z, and then I can also solve the second equation for y in terms of z. So if you subtract z from both sides of the first one, the equation you get is x equals 2 minus z, and the second equation will give you y equals, after you add z to both sides, is going to be 2 plus z. So in other words, if you take any real number that you want, you can plug that in for z and make that be the z coordinate of the point, and these two equations will tell you how to get the corresponding x and y points. So here's what that looks like here. I set up a slider here that will give you a different value of z, and I set up the point, that black point here, so the x coordinate is always going to be 2 minus z, and the y coordinate was going to be 2 plus z, and changing that z coordinate keeps your x and y coordinates correct so that you stay on the line and you stay within the solution set of the system of equations. So to actually write the solution set in parametric form, it means we're going to write x, y, and z each in terms of a parameter variable t, which is just a new variable we're going to introduce, and we're going to try to write some kind of 3 equations for x and y and z in terms of t. But we already have x and y in terms of z, so the easiest thing to do is just to say that x can be equal to 2 minus z, but write z as t, and we have y as 2 plus t, and just say that z equals t. And it's really the same thing as what we had before. We're just basically introducing a change of variables. And then when we want to talk about the points, we can write it like this. We can say that the points x, y, z are, the x is 2 minus t, the y is 2 plus t, and the z is just t, and that is what we mean by parametric form.